Hello and welcome to our Wednesday webinar from the IEA Clean Coal Center. My name is Benedicta and I'm part of the communications team here. Our monthly webinars are based on our technical reports, which are available from our website, www.iea-coal.org. Residents of member countries and employees of sponsoring organizations can download our reports at no charge after a one-off registration. The subject for today's webinar is Digital Transformation of Coal Power Generation, presented by Dr. Qian Zhu. The report on this topic will be published in the autumn. Go ahead, take it away, Qian.
Thank you, Benedicta. And hello, everyone, and thank you for tuning in to today's webinar on digital transformation of coal power generation. First, I would like to give a brief introduction to our center. The IEA Clean Coal Center is a technology collaboration program mandated by the International Energy Agency, IEA. We provide independent information and analysis on all coal-related trends. We promote best practice in all aspects of coal production, transport, processing, and utilization. We address the role of coal in the energy trilemma and the need to balance security of supply, affordability, and environmental issues. We are funded by national governments and by corporate industrial organizations. Here is the outline of what will be covered in today's webinar. I will first talk about the ongoing energy transition and the challenges it poses to power industry, in particular to coal-fired power plants. I will then discuss the key digital technologies for digitalizing coal power generation. Other digital tools that can enhance digital transformation of coal power will also be described. Next, I will talk about the digital transformation of power generation, and this is followed by potential benefits and barriers to digitalization of power plants. And finally, conclusions are drawn to wrap up today's webinar. If you have any questions, please type them in the question box where we go along, and I will answer your questions at the end. Global energy systems are currently undergoing fundamental changes that can be described as 3Ds: decarbonization, decentralization, and digitalization. The rapid deployment of many clean energy technologies in recent years accelerates the decarbonization of global energy systems. Over the past decade, there has been a significant rise in installed capacity and the generation from renewable energy sources. In 2018, a total of 181 gigawatts of renewable power was added, bringing the global total installed capacity of renewable power to around 2,378 gigawatts and accounts for 1/3 of total installed power generating capacity. It is forecasted that by 2050, renewable sources will provide 2/3 of the world energy, with wind and solar power make up 48% of total global electricity generation, compared to today's 9%. With the rapid development of solar and wind power, there has been a move towards decentralization with increased distributed power generation where the electricity is produced at or near the point of use to meet local power demand. Also, as rooftop solar installation surged over the last decade, more consumers have become energy producers, the so-called prosumers. Digital technology have been applied within power industry for decades. The trend towards greater digitalization has been enabled by recent developments in a range of digital technologies, such as advanced analytics, Internet of Things, artificial intelligence, AI, and machine learning, and a faster communication network. Digital transformation is occurring across the energy value chain, from generation through transmission and distribution, all the way to end users in homes, factories, and businesses. The traditional power system has been built on large centralized power generation and a one-directional grid that delivers electricity from power plants to end users. With the energy transition, the grid will have to host more variable renewable power, rising levels of distributed energy source and energy storage, triggering two-way power flows within the transmission and distribution system. This means there is a need for an efficient, flexible, and reliable grid that can cope with increasingly dynamic and complex two-way energy and information flows. The development of renewable power has forced many coal power plants that were designed for baseload generation to operate increasingly at cycling mode or partial load with rapid load changes. Today, coal-fired power plants face four major challenges. First, they must improve operating efficiency to meet efficiency and regulatory target and be competitive with natural gas and renewable power. Second, they must reduce oil emissions to minimize the environmental impact of coal combustion. Third, they need to be more flexible so they can ramp up and down rapidly and cycle on and off to balance the grid while remaining profitable with limited operation time. And last, there is a need to reduce unplanned downtime and improve reliability, especially when operating in a cycling mode or at low load, as well as to reduce operation and maintenance costs. Digitalization of power generation requires many digital technologies, including big data, analytics and AI, digital twins, cloud, and cybersecurity. Big data refers to the generation, storage, processing, verification, and analysis of large, highly versatile and fast-growing volumes of data with the objective of creating valuable information. The data collection capabilities provided by process instrumentation embedded with electronics and sensors, coupled with improved method of networking and storage, have enabled power companies to accumulate vast amount of time series data from power plant operations, laboratories, suppliers, and other sources. Together, this data contain potential insights into the operation and the maintenance of virtually every major item of equipment and every important process in the power plant. The challenge for power generators is to make this data useful and generate actionable insights from it. Big data analytic tools and platforms have been developed to harness this data to help power producers make informed decisions. Many power companies have actively adopted big data analytics. Typically, the power generators with large fleets are the early adopters. Analytics is a part of data science that uses modern technology and tools to focus on projecting future trends, events, and behaviors. Advanced analytics comprises several subfields of analytics, such as predictive analytics, data mining, big data analytics, and machine learning that work together in their predictive capabilities. Advanced analytics employs modern technologies such as machine learning and AI, deep learning and neural networks, and visualizations. Today, AI is based on a variety of disciplines, including mathematics, statistics, cognitive science, philosophy, and linguistics. Advanced analytics is at the core of the next generation digitally transformed power generation that enables intelligent operations. Big data and advanced analytics can provide power producers with insights on the state and the performance of assets, processes, and operations within a plant and system-wide, help them to make better, faster decisions and to maximize the plant's operational efficiency while responding optimally to changing conditions on the grid and in the overall power market. In recent years, there has been significant progress in the development of industrial analytics. Today, analytics solutions for control and optimization of power plants operation are commercially available from well-established power generation equipment suppliers, such as ABB, GE, MHPS, and Siemens, as well as software companies like Seek and many more. For example, GE's digital power plant solution is a suite of analytics and control applications integrated into GE's cloud-based digital platform, Predix. It consists of operation optimization, assets performance management, in short APM, and business optimization services. Operations optimization comprises several subsystems such as fuel supply management and boiler optimization that provides key performance indicator-focused analytics. Operations optimization delivers proactive recommendations by analyzing internal plant data, historical operational data, or external information to inform key resources, reduce production costs, and enhance plant flexibility. APM is a cloud-based software application designed to increase asset reliability and availability while reducing maintenance costs. GE's APM connects disparate data sources and uses over 300 physics-based models and statistical software analytics to turn that data into actionable insights. GE's APM has 3 modules: machine and equipment health, reliability management, and the maintenance optimization. The machine and equipment health monitors state and health of each and every asset, provide clear guidance on the next occurrence as well as the asset history. Reliability management uses various analytic tools to predict and diagnose issues and respond before they negatively impact operations. Maintenance optimization delivers proactive recommendations to optimize preventive maintenance strategies to balance reliability, availability, performance, and costs against risk. The business optimization is designed to help power producers to take full advantage of predictive analytics to make improved decisions in all business areas. Another example is Japan's MHPS. It developed a cloud and edge-based digital platform, Tomoni, which consisting of 3 layers: the ICT foundation, high precision AI application, and the service applications as shown in the figure on the left of this slide. The analytic tools are implemented in the layer of high precision AI application that sits in the cloud. The analytic engine covers asset performance models and asset life models enabled by high precision cognitive AI applications. Performance models include advanced pattern recognition, thermal efficiency models, and expert system. Life model consists of remaining life analysis, reliability, availability, maintainability analysis, and the maintenance of enterprise asset management. The analytic tools are seamlessly and securely connected to machine sensor data and the databases such as the fault tree analysis database. Combining big data with analytics and control, the digital platform enables MHPS to deliver service solutions on operation and maintenance optimization, performance improvement, and flexible operation. A digital twin is a virtual representation of a physical asset, process, or system that captures attributes and behaviors of that entity, suitable for communication, storage, interpretation, or processing within a certain context. It consists of sophisticated models based on deep domain knowledge of specific industrial assets. A digital twin compresses data, computational models, and the service interfaces as shown in this slide. The core element of a digital twin is information, which is related to each life cycle phase of the underlying entity and is seamlessly made available between phases. A digital twin can serve as the foundation for advanced analytics and AI applications. Today, numerous digital twins for power generation processes are available in the market. They are from traditional power generation technology suppliers such as ABB, GE, and some software companies like IBM and SEEK, as well as utility engineering companies include Uniper, Honeywell, and Bentley Systems. This slide shows an example of power plant digital twin developed by GE. It integrates a collection of high-fidelity computational physics-based models and advanced analytics that focus on various areas of power generation processes. GE claims that applying its digital twin can unlock up to 8 to 13 megawatts of capacity from improved plant efficiency, reduce startup time by up to 50%, reduce unplanned outages, saving the generator up to $100 million per year, and up to 10% reduction in maintenance costs. Digital twins can have a wide range of applications such as design verification, system testing, and operator training. They can be connected to database and real-time operational data to represent accurately the present state of assets, processes, and the power plant. enabling engineers and operators to predict the plant's performance, evaluate different scenarios, understand trade-offs, and enhance efficiency. For example, Amazon of USA developed a digital twin that is the exact replica of the plant control system and can be used as a non-production testbed to validate control logic and the security patch updates. In 2015, the US Platte River Power Authority replaced a mix of distributed control systems and programmable logic controllers at its 300 megawatt coal-fired power generating units at the Rawhide plant with a single Ovation platform of Amazon. The platform is used to monitor and control critical plant processes, including FGD scrubbers, balance of plant, boiler, steam turbine, data acquisition, fuel handling, and water treatment. After installation, the digital twin simulator enables the plant engineers to conduct control logic testing and patch verification, and to train plant operators. In the first 4 months operation, operations completed 400 man-hours of simulator training, which led to a 44% reduction in the time operators required to perform plant startup and shutdown scenarios. The cloud computing is the delivery of on-demand computing services over the internet cloud, typically on a pay-as-you-go basis. Cloud computing offers faster innovation, flexible resources, and economy of scale, and can help users run their infrastructure more efficiently at lower operating costs. Last year, more than 150 utility companies around the world were surveyed. 94 of the companies were power utilities. The survey found that 71% of the utilities were already using cloud services, and the pace of adoption and the breadth of applications being moved to the cloud has accelerated in the past 3 years. This trend was set to continue as 74% of the utilities surveyed said they plan to spend more on cloud computing in the next 3 to 5 years. As digitalization advances, power plant operation become increasingly dependent on ICT, which increases the risk of cyber attacks. The IEC identified 5 cybersecurity approaches for smart energy. Among them, security by design is the most cost-effective one for cybersecurity. Hardware and software have been developed and implemented to protect energy infrastructure. Digital solutions adopting AI and machine learning for enhanced cybersecurity are under development. The next generation cybersecurity system will have built-in knowledge-based systems and the machine learning technology that could find a pattern in network packets and block them automatically if flagged as threat. Blockchain, which will be discussed next. Blockchain is considered a promising technology that could help improve cyber defense. Work is ongoing to develop blockchain technologies to strengthen cybersecurity and to identify the information operators need to respond under multi circumstances. Other digital tools such as blockchain, robots, and unmanned vehicles smart goggles or head-mounted display and cameras are being developed or under development and can play a role in digital transformation of power plants. Blockchain is a type of distributed ledger technology. Multi-computer systems are used, and any change to the data require consensus from all parties contained in the blockchain, making it difficult to destroy or tamper with. So data written to the blockchain is very secure against hacking. Blockchain can potentially play a key role in energy trading and cybersecurity. Robots can be used to perform inspection, maintenance, and repair work at dangerous or difficult to reach areas or sites of power plants, such as inside a boiler, stacks, and towers. The bottom left figure shows the GE's robotic crawler used for boiler water ward cleaning and inspection. Using drones and robots can limit or eliminate the need to send workers to risky, time-consuming tasks and hard-to-reach assets, leading to improved health and safety standards and saving on operation and maintenance costs. 3D printing has already successfully produced parts for commercial nuclear and gas-fired power plants. The bottom right figure shows the 3D printed components for a prototype nuclear reactor developed at Oak Ridge National Laboratory of US DOE. 3D printing could, in future, enable power generators to produce some parts on site when they are required, eliminating the need to store the spare parts on site and thus reduce costs. Digitalizing a power plant is a wide-ranging exercise based on the 5 key functions listed here. Today, the ever faster and ubiquitous connectivity provides the foundation of a digital power plant by enabling the connection of sensors, devices, assets, and people. The Internet of Things provides the building blocks of a digital power plant, allowing for collection, transmission, analysis, and management of operations, processes, and assets data. Software provides tools to analyze and identify, predict any issues, and determines the appropriate actions with real-time responses to resolve or prevent the problems, and to maximize the performance and profitability potential of assets, plants, and fleets. There are 3 focus areas for power plant digital applications: operation performance management, asset performance management, and field service management. OPM is a digital solution that provides critical decision support and improves plant efficiency, productivity, and flexibility by using software that understands a machine's physical capabilities relative to its theoretical potential. Advanced analytics and control can detect any deviations from set points and adjust operating parameters in real time to optimize operational and environmental performance and minimize production costs. A comprehensive APM approach comprises 4 important components: monitoring, diagnosis, prediction, and action. Each asset has condition data measured and recorded to monitor their health and the state of operation. By determining overall asset health, APM software detects any anomalies or operational issues, assess the likelihood of asset failures, identifies their respective root causes and resolution, and the likelihood of the asset failures, identify the respective and recommend the quick actions for their resolution. Consequently, forced outages are minimized. APM enable power plants to shift from the current preventive maintenance system to a predictive or condition-based maintenance, and hence the uptime is increased. The lifetime of assets and the power plants are extended, leading to reduced operation and maintenance costs and the improved economic value of the plant. In the event of an unforeseen repair or outage, or APM monitoring and diagnostics recommending an actionable maintenance task. By relying on data from remote sensors, power producers can pinpoint where to send the crew for a repair, and based on the assessment of the damage, ensure the team arrives with the right tool for the job. When needed, the smart devices connect the service workers to a remote expert, enable the remote expert to see what the workers see, and can guide them to perform the necessary inspection, tests, and repairs. Robotics may be used to perform inspection, maintenance, and repair activities, reducing repair time and saving on operation and maintenance costs. Digital twins are behind the OPM and the APM applications of digital power plants. Digital twins model the state of every asset process in a digital power plant, as well as the whole plant and the fleet, starting by providing guidance on design limits of a power generating unit at the commissioning stage, to the state of real-time operation throughout its lifetime. Digital twins also provide tools such as operator training, design and system testing and validation, and running what-if scenarios. In addition, digital tools for intelligent forecasting, portfolio optimization, and trading can help power producers to make smart business decisions around power trading, fuel purchases, and portfolio management to reduce the financial risk and maximize the profitability of their fleet and enterprise. Digitalizing power plants represents a step change in improving operational, environmental, and economic performance. Studies show that digital technology could improve efficiency of coal power plants by 2 percentage points. CO2 emission savings of 469 million tons per year, or 4.2% global CO2 emissions, could be achieved if all existing coal-fired power plants around the world were digitalized. The IEA estimated that the overall savings from digitalization could be in the order of $80 billion a year over 2016 to 2040, or about 5% of total annual power generation costs, based on the enhanced global deployment of available digital technologies to all power plants and the network infrastructure. In this, a 5% reduction in the operation and the maintenance costs of power generation and electricity networks could result in total savings of $20 billion per year over 2016 to 2040. The popular perception of utilities as analog era companies makes it difficult for them to attract digital talent, such as data scientists and people with specialized IT skills. Given the size, complexity, and the lifetime of power generation systems, some companies may find it difficult to identify where to start digitalization or are unclear of their objectives and the priorities. Cybersecurity is a concern for power producers, especially when considering adopting cloud. Furthermore, digitalization requires large capital investments. For existing coal power plants that are old, or those profitability is squeezed due to competition from gas and renewable power, the plant owners are reluctant to commit to large investment if there is no clear path to a return on it. All these factors can hinder the pace of digital transformation of coal power plants. So to conclude, the connection, monitoring, analysis, prediction, and optimization are the foundation of power plant digitalization. The future intelligent power generation will be a data-driven, cloud-enabled enterprise. Power generation will be run on a digital platform which is connected to almost everything from across the energy value chain and beyond. Big data and AI-powered advanced analytic tools linked to the digital platform will enable power producers to analyze, learn from, and act upon the data, and to make informed decisions in all areas of their business. The digital platform can run the complex power generation operations efficiently, leading to optimal operational and environmental performance, improved flexibility, reliability, security, and profitability. Digital technology can significantly improve plant efficiency and potentially reduce CO2 emissions and the cost of power generation substantially. Thank you for your time. And now I can take some questions. Let me see if there are any questions here. Right. I've got a question here. It is known that renewable electricity sources have a variable character. From this point of view, and for reasons of security of power supply, should coal-fired power plants be considered in the emergency mix, at least in the medium term? Oh yes, the coal-fired power plants are needed to, especially in countries where there is limited gas and oil resources. So coal will provide, will play an important role and provide will be used to stabilize the grid for the near and the medium future, that's for sure. There's another question here. Oh, that's the same one. To what extent is China adopting this network monitoring and control system? Oh, sorry, I haven't looked into this. I just In my report, I just reviewed the technologies development, what technologies available and are under development for the future digital power plants. But no, I haven't looked at into, you know, the extent in China, the adoption in China, you know, to what extent they are using it. No, I have no idea. Another question, does digital technology alter the balance of commercial advantage between the OEM and the end user? I don't quite understand what this question is about. Can we does digital technology alter the balance of commercial advantage between OEM and end user? I'm sorry, I don't quite understand this question. Right, let's move on to the next one. You can email me and we can discuss this over, but yeah, let's move to the next one. Can you talk about rollout of this digital transformation in coal power plants in China? Again, I haven't looked at the China's application of digital technology, so I have no idea. The next question is, how reliable is digital twinning? At the moment, the digital twins is used for like running simulations. So like used for operator training, used for non-productive what if scenario test. It hasn't been used for actually, you know, replica the operation, or maybe it has in certain extent, but not for the whole plant. For some asset, the digital twins is used for monitoring the operation, but mostly it's being used to run system testing or run the what if scenarios of the operator trainings. Right, the next one is yeah, next one is coal power plants in China in certain provinces. For example, Sichuan, where there is abundant renewable energy resources, are heavily underutilized, making it financially challenging to operate. Do you think such potential digital transformation could change that trend? Yes. The digitalization could make the coal power plant running more flexibly to accommodate the renewable power. So yeah, the answer is yes. Right. I think this is the last question. If the OEM supplies the digital technology, Does that give the OEM opportunity to make greater profit? Right. The last one says, thank you. It was very interesting webinar. It's not a question. It's a thank you, Gabrielle. Yeah.
Great. Thank you. I think that's all we have time for today.
Yeah.
And thank you so much, Qian. And as Qian said, if you have more questions, you're always welcome to send them via email. And yeah, as I said, the report on this topic will be published in the autumn, and the slides from the webinar will be available to download from our webinar page shortly. All that's left for me to say is the next webinar from us will be in August on Wednesday the 5th, and it will be presented by Dr. Andrew Mentioner. Thank you so much for all of you for joining us today, and goodbye.